Okay, so in this video we're going to carry on from where we left off in the last. So let me begin by reminding you what the main takeaway was from the previous video. The main result was that it is possible to construct an ordered field that we call R. This is the set of real numbers, which satisfies the LUB property, right? And importantly, R contains the set of rationals as a subfield. Okay, so what the result means is that we already know that Q is an ordered field, okay, which means that it has the familiar notions of ordering, addition and multiplication that we are used to. However, Q, as we have seen, does not satisfy the least upper bound property. It is so what the result tells you is that it is possible to quote unquote extend Q, right, to an ordered field R, right, such that Q is a subfield of R. What does it mean to say that Q is a subfield of R? It means that the notions of addition, multiplication and ordering within R is consistent when restricted to Q. Okay, and most importantly, this extension R satisfies the LUB property, unlike Q. Okay, so moral of the story is that it is possible to extend, quote unquote, complete the rationals, by incorporating the numbers that we of course understand as the irrationals, such that the new and completed ordered field R now satisfies the LUB property. As I said, we are not going to go into the proof of this result itself. I invite you to take a look at the first chapter of Rudin if this is of interest to you. What I'm going to do in this video is basically tell you some of the consequences of the fact that R is an ordered field that satisfies the LUB property. Okay, and these are things which one cannot necessarily say in Q, but because R satisfies the LUB property, one can. Okay, so the first of these results is the following. Okay, so the first result tells you that if x and y are real numbers with x being positive, I can always find a positive integer n such that when n is multiplied by x, it actually exceeds y. Okay, seems fairly intuitive. You should, of course, this should seem very natural to you. We will actually use this property to prove other properties that are far less obvious. This is in fact called the Archimedean property. Okay, so if you have any two real numbers x, y, x being positive, I can always find a positive multiplier, a positive integer n, such that n times x becomes larger than y. So that's the first part of this theorem. The second part of this theorem is that if x and y are two real numbers with, let us say, x less than y, then there exists a rational between x and y. Let's say there exists P in Q such that x less than P less than y. Okay, so this is actually a fairly non-trivial result. It tells you that if I take any two real numbers, there is a rational between those two real numbers. Right? Now, if x and y were themselves rational, then this is obvious, right? We already talked about this before. There is always a rational between two rationals. But now we are saying there is a rational between any two real numbers, right? So this property is basically an expression of the fact that Q is dense in R. Okay, now dense is actually a measure theoretic term, so I'm not going to get into details about why, but at this point it's sufficient if you just understand this in an intuitive sense. If between any two real numbers there is a rational, that means that the rationals are quote unquote dense within the set of reals, right? So that is what the second part of this result tries to prove, tries to say. Alright, so now let us see how we are able to prove these things using the theorem that we started with, which is that R is an ordered field which satisfies the LUB property and R contains Q as a subfield. Using this, how do I prove these two statements? Alright, so let's begin by proving part A. Now here, suppose that the claim of the theorem is not true. That is, suppose there does not exist an n such that nx is actually more than y. Okay, so suppose claim is not true. Now, what does it mean to say that the claim is not true? If the claim is not true, what that means is that for every n, nx should be less than or equal to y. Correct? So, y should in fact be an upper bound for every number of the form n times x. So let us take that claim further. So, let us say that A is the set of all numbers n times x such that n is a natural number. Okay, so since claim is not true, y is an upper bound on this set because for all n, nx should be less than or equal to y. The claim, since claim is not true, y is an upper bound. On A. Alright. Now, what does it mean? It means that A is a non-empty set which is bounded from above. Because R satisfies the least upper bound property, if you have any subset of R which is bounded from above, it must also have a supremum. So, which means that alpha is equal to supremum of A exists. Right, so this means that there is a least upper bound to this set A. Now, what does that in turn mean? If alpha exists and it's a least upper bound, that also means that alpha minus x is not an upper bound. Okay. Now we are getting to our contradiction shortly. If alpha minus x is not an upper bound on A, that means that there exists some, let's say, integer natural number m such that mx is actually more than alpha minus x. Because after all, alpha minus x is not an upper bound, right? Which means there is an element of the set A, I'm just calling it m times x, which in fact exceeds alpha minus x. And this of course is the same as saying that m plus 1 times x is more than alpha. Okay, so that's our contradiction, because if m times x is an element of A, so clearly is m plus 1 times x, and we just said that m plus 1 times x is more than alpha, but alpha was supposed to be the least upper bound of the set, right? So which means alpha itself was supposed to be an upper bound, but I found an element of the set which actually beats alpha, and that's your contradiction. Right, so that proves that our original, that shows that our original claim is in fact not true, and so there must in fact exist a positive integer n such that nx is more than y, right? And that proves the Archimedean property. So it's a fairly straightforward result, and the main idea of the proof is that if this result is not true, then the set A that we have defined here, which is the set of all multiples, the set of all natural number multiples of x, that set where x is a positive number has to be bounded from above, right? And then we said that, okay, that's a contradiction, because if it is bounded from above, it must have a least upper bound. But you know, I can always come up with, if alpha is a least upper bound, I can come up with an explicit element of the set which actually becomes greater than alpha. That's your contradiction. Okay, so that's how you prove the Archimedean property. Now let us try and prove the second result, which is perhaps less obvious to begin with, namely that there exists a rational number between any two real numbers. Okay, so now this is the proof of part B. Okay, so I'm going to use the part A, the Archimedean property, repeatedly in proving this. So from A, there exists an n in the naturals such that n times y minus x is greater than 1. Okay, so this is basically the Archimedean property where I have used y minus x in place of x and 1 in place of y. Okay, so convince yourself that because y minus x is positive, remember we are looking at two real numbers x and y such that x is less than y, right? So because y minus x is positive, from the Archimedean property, there must exist a natural number n such that n times y minus x is more than 1. Okay, now similarly, from the Archimedean property again, there exist again natural numbers m1 and m2 such that the following are true. M1 is greater than n times x and M2 is greater than minus n times x. Okay, so n is what we got from the first application of the Archimedean property. Now we are going ahead and saying that if I take nx, this is a comma, if I take nx as y in the Archimedean property and if I take x to be just 1, I can always find a natural number m1 such that m1 exceeds nx, right? Similarly, if I take minus nx as y, then I can always find a natural number m2 such that m2 is greater than minus nx as well, right? So these are again natural applications of the Archimedean property. But what this means is the following. So if you take these two inequalities together, what that means is that minus m2 is in fact less than n times x, which in turn is less than m1, right? So what this has really shown, the second and the third application of the Archimedean property, what it has shown us is that it is in fact possible to sandwich n times x between two integers. Now it might seem to be obvious to you that okay, well, any real number should be sandwichable between two integers, but I don't think it's obvious so long as you think of nx as a rational number. Once you're talking about the reals, nx could well be irrational, right? So what this really has shown is that if you give me any irrational number, I can sandwich it between two integers, right? Because m minus m2 is some integer, m1 is another integer, right? And once I have proved that it is possible to sandwich nx between two integers, it turns out that you can also inductively show that you can sandwich it between two successive integers. Specifically, there exists an m, let's say in actually this m doesn't belong to the naturals. This m actually belongs to the set of integers. There exists an m in the set of integers such that m minus 1 less than equal to nx less than m. Okay, so this is something that again I want you to think about, right? What have we really started with? We have started with this statement that nx is sandwiched between two integers, let's say m1 on the right and minus m2 on the left. Now what I can do is inductively, move the right end, the upper bound left and the lower bound right. Okay, so I can then ask, well, is nx is clearly less than m1, is it less than m1 minus 1? Well, if so, then I'm going to replace m1 by m1 minus 1. Then I ask, is it less than m1 minus 2, right? And I keep going this till I get a no. So which means I keep pushing the upper bound left to the extent I can. Similarly, I keep pushing the lower bound to the right to the extent I can. And in the end, I'm going to end up with two adjacent integers such that nx is in fact greater than or equal to m minus 1 and less than m. Okay, so this kind of sandwiching is in fact made possible by the initial statement that it is in fact nx is in fact sandwiched between two integers in the first place. Okay, and now that almost brings us to the end of this proof. So this nx, okay, is less than m. That comes from this part of the bounding, which then this m in turn is less than equal to 1 plus n times x. That comes from this part of the bound. Alright, and now if I go back to my original application of the Archimedean principle, 1 plus nx is in turn further less than n times y. And that, if you stare at it a little more, in fact implies the statement of the result. Why? Because if I look at the first inequality here, nx less than equal to m, that implies that x is in fact less than m by n. Okay, here it's important that n is a natural number. It's only because it's a positive number that I'm allowed to quote unquote divide on both sides of the inequality. And if you look at this patch together with this, that m is in fact less than ny, you also will realize that m by n is less than y. So we have now constructed, okay, remember I don't know if m is positive or negative, but n by construction is positive because it's a natural number, right? M is some integer, okay? So we have constructed this rational number m by n such that m by n is more than x and less than y. So which means that we have found a rational number which lies between x and y. Okay, so the proof is not difficult, but yeah, this is something that if you haven't seen this before, you have to go through this a few times to convince yourself that, you know, the arguments make sense, right? And it may not be obvious, I mean, it may not have been obvious to begin with that in fact a property that seems so natural, namely the Archimedean property, can actually prove something far more non-trivial, which is that between any two real numbers there exists a rational. In other words, the rationals are dense in the reals. Okay, and all of this is a consequence, if you think about it, of the LUB property of the reals, right? Because our original Archimedean property itself was proved using the fact that R satisfies the LUB property. All right. So that is the first main result that I wanted to highlight as a consequence of the fact that R satisfies the LUB property. There is now one more result that I'm going to prove, which is further an illustration of the power of the LUB property. Okay, the result is as follows: for any real x which is positive and any natural number n, there exists a unique real y greater than 0 such that y raised to n is equal to x. Okay, so this in fact goes back to one of the first statements we made about the rationals, if you remember, right? We said that there does not exist a rational, for example, that satisfies y square is equal to 2. But this is a more general statement. I'm saying let x be any positive number, not necessarily 2. Let n be any natural number, not necessarily 2. There always exists a positive real number, which is unique, in fact, which satisfies y raised to n is equal to x, right? So in other words, for any positive number x and for any natural number n, it is meaningful to talk about the so-called nth root of x. So in fact, we call y or we refer to y as x raised to 1 by n. Right? So not just the square root of 2, the nth root of any positive number in fact exists within the set of reals. Okay, so this is in fact a property which, as we already know, does not hold within the rationals, but now we are going to show that because the reals satisfy the least upper bound property, this in fact does hold. Okay, so yeah, stare at the theorem statement a couple of times to make sure that you understand what exactly it is trying to say. And now let us get into the proof. Okay. So the first observation that we are going to make is fairly straightforward. Firstly, that if there was to be a solution, now we are looking for a solution of, in y of the equation y raised to n is equal to x. The theorem says that in fact there is a unique positive solution to this equation, right? The first statement we are going to make is that there can be at most one solution. You definitely cannot have more than one solution to this. Now, why is that? That follows from basic monotonicity arguments. There is clearly at most one solution to y raised to n equals x. This is because if y1 is greater than y2, which is greater than 0, then y1 raised to n will in fact be greater than y2 raised to n, right? In other words, if I take any, so what this tells you is that if y1 and y2 are positive such that y1 is greater than y2, then y1 raised to n is in fact greater than y2 raised to n. I invite you to go back and prove this using only the axioms of the ordered field, right? So this is really a consequence of the fact that R is an ordered field. Okay, so that means that clearly there can only be at most one value of y such that y raised to n is equal to x, because for any two distinct values of y, let's say y1 and y2, y1 raised to n and y2 raised to n could not possibly take the same value. Okay, so there is clearly at most one solution. Now we have to show that there is in fact one solution. Okay, so for this, let us define the set E as follows. E is the set of all t in R plus. This is the non-negative reals. Okay, such that t raised to n is less than x. Okay, so I'm going to define the set E as the set of all non-negative reals that satisfy the property that that real number raised to n is in fact strictly less than x. Okay, now I want to argue that this set is in fact bounded from above, and later we are going to show that because it's bounded from above, there must be a least upper bound for the set, and that least upper bound is in fact the value of y, the solution of y raised to n is equal to x. That is where we are headed. But before proving that, first I have to of course show that this set is non-empty in the first place, right? So first let us show that E is non-empty. How do I argue that E is non-empty? So suppose I define T is equal to x upon 1 plus x, right? X, remember, is given to you as part of the problem. If I define T as follows, clearly that this T is less than 1. Okay, again, straightforward consequence of the fact that R is an ordered field. Okay, if x is positive, then x by 1 plus x must be less than 1. I leave that for you to check. Similarly, x by 1 plus x is also in fact less than x, but we'll see. So this implies that t raised to n is in fact less than t, right? This follows from the fact that t is less than 1, right? And then further t is less than x. Okay, what is the meaning of all of this? This means that this particular t belongs to E. Implies that E is non-empty. This is just to show that this set we have constructed of non-negative reals whose nth power is less than x is non-empty, right? The set khali nahi hai. That is the first thing to note. The next thing to note about E is that in fact it is bounded from above. So the way to see this is that if you look at 1 plus x is of course greater than 1. So 1 plus x raised to n is in fact greater than 1 plus x. This comes from the fact that 1 plus x is, as I said, more than 1. And 1 plus x in turn is greater than x. Okay, this means that 1 plus x is an upper bound on E. Because the number 1 plus x satisfies the property that 1 plus x raised to n is in fact greater than x. So you can now go back and convince yourself that 1 plus x is in fact therefore larger than every element of E. In other words, so if you combine these two things, what we have said is that E, the set that we have defined here, is in fact non-empty and bounded from above. Now, because because R satisfies the least upper bound property, that means that the supremum of E must exist. Okay, so let me denote that by Y. Okay, so we know that a supremum exists. What we will show now is that Y in fact solves the equation that I began with, which is to say that we will prove that Y raised to n is equal to x. We will now show that Y raised to n is equal to x. Okay, now how do I prove something like this? How do I prove that Y raised to n must be x? Well, what we will do is prove that Y raised to n cannot be less than x and it cannot be more than x. Okay, so we will do this by showing that Y raised to n greater than x and Y raised to n less than x are not possible. Right, and again, why does this imply the result that Y raised to n must be equal to x? Because of the fact that the reals are an ordered field, which means that any two elements which are not equal, must have either one of them being greater than the other, right? So if Y raised to n is not more than x and if Y raised to n is not less than x, then Y raised to n really has to be equal to x, right? So this is what we need to prove, right? So what all that remains to show. So let me, before I move to the next page, let me quickly recap the style of the proof so far. We defined the set of E as follows. This is a set of all non-negative reals which has the property that the nth power is less than x. Okay, we showed that this set E is non-empty and bounded from above, and so it must have a least upper bound or supremum. Okay, then we are just going to go about and show that that least upper bound or supremum is in fact the solution to the equation Y raised to n is equal to x. Okay, so we are just denoting the supremum by y, and we are going to show that Y raised to n greater than x and Y raised to n less than x are not possible. Okay. Okay, so let's start with case 1, that Y raised to n is in fact less than x. So we are going to show that this is not possible. Okay, to show this, I am going to use a particular inequality which you are probably quite aware of, and that's the following. For b greater than a greater than 0, b raised to n minus a raised to n is less than b minus a times n times b raised to n minus 1. So yeah, I'm not going to prove this. It's a trivial exercise for you. Please go back and check that using only the basic addition and multiplication axioms on the reals, you should be able to show that if a and b are positive real numbers satisfying this, that b greater than a, then in fact b raised to n minus a raised to n can be upper bounded by b minus a times n into b raised to n minus 1. Right? So this is not difficult. So I'm going to use this result going forward. Now suppose that, okay, now let's come back to the case we are trying to address. We want to show that if y raised to n is less than x, then we want to contradict the fact that y is in fact the supremum of the set E. Okay, and how are we going to do this? We are going to show that if y raised to n is less than x, I can come up with a number which is larger than y such that its nth power is also less than x. Okay, and if I can do this, that contradicts the fact that y is supposed to be an upper bound on the set E. Okay, so let's see how we are going to do this. Let h be in 0, 1 such that h is in fact less than x minus y raised to n upon n times y plus 1 raised to n minus 1. Okay, so remember y raised to n is in fact less than x. Okay, so therefore I can talk about x minus y raised to n as a positive number, and I'm saying that find a number h between 0 and 1 such that h is less than x minus y. So all I need really is that this fellow is positive. For any positive number, I can find another positive number between 0 and 1 which is less than that number, right? That is all I'm saying. That's not difficult to show. So I can define an h such that h is less than x minus y raised to n upon n times y plus 1 raised to n minus 1. Why am I doing this very contrived construction? You will see that in a minute. Now let me look at y plus h raised to n minus y raised to n. Okay, for this I'm going to use the inequality in the box here, where b is y plus h and a is y. So this is therefore less than h times n times b. b in this case is y plus h raised to n minus 1. So this follows from the inequality that we wrote before. Okay, now let us use the property of what exactly this h is. Let me stare at that for a second. Now because h is less than 1, I can further upper bound this by n times h times y plus 1 raised to n minus 1. Right? This of course comes from the fact that h is less than 1. Okay. Now if you stare at this, it's n times h times y plus 1 raised to n minus 1. This in turn, from the inequality that we have written just here, from inequality number 1, is further less than x minus y raised to n. Okay, so the end conclusion of this string of inequalities is that y plus h raised to n is in fact less than x. Okay, and what does that mean? That y plus h also belongs to E. But this contradicts the fact that y is supposed to be an upper bound on E. This is contradicting the fact this statement that y is in fact the supremum of E. Because if y is the supremum of E, you couldn't possibly find an element which is more than y that belongs to E. Okay, so this is how you show that it is not possible that whatever supremum you had of E, let's call that y raised to n is less than x. This is not possible. In other words, case 1 is not possible. Now let's move on to case 2. That y raised to n is in fact more than x. Now if y raised to n is more than x, we are going to show that, well, there is always some number which is less than y whose nth power is also more than x, right? Which implies that that smaller number is also a valid upper bound on E, which of course contradicts again the fact that y is the least upper bound of E. Okay, so let us see how that works. The construction is in fact going to be very similar. We are going to use the same inequality in the box up here. Now I'm going to define k as follows. K is y raised to n minus x upon n times y raised to n minus 1. Why this particular construction? Again, it is basically meant to exploit this inequality. Okay, so once again, y raised to n minus y minus k raised to n. K is positive, remember, right? So y minus k raised to n is in fact less than b minus a, which is k, times n times y raised to n minus 1, right? Which by the inequality number 2 is in fact less than y raised to n minus x. So therefore what we have really proved is that y minus k the whole power n is in fact greater than x, which implies that y minus k is an upper bound. But this clearly contradicts the fact that, contradicts the earlier statement that y is the least upper bound on E. This contradicts y is equal to supremum or least upper bound of E, and that gives us a contradiction, right? So we have shown essentially that that number y, which was the supremum of the set E, cannot possibly be such that its nth power is less than x. It cannot possibly be such that its nth power is more than x. Put all of these together and we can now conclude that y raised to n must in fact be equal to x. Okay, so that really is the way you prove that while in the rationals it is not always possible to find the nth power of a positive number, within the reals it is always possible to uniquely define the nth power the nth root of any real number. Okay, so and again, if you go back to the proof, you will see that the proof depends very heavily on the least upper bound property. So given only the fact, see, remember, I haven't actually told you very much about how I'm formally defining, say, addition between irrationals, multiplication between irrationals, multiplication and addition and ordering between rationals and irrationals. So none of those details have been laid down. But just the fact that there exists an ordered field, which is a superset which contains the rationals as a subfield and which satisfies the least upper bound property, we are able to prove all of these remarkable things. Namely, that in this particular result told us that, you know, for any positive number and for any natural number n, the nth root is well defined. Okay, so it's always possible to find a y such that y raised to n is equal to x. Okay, so I'm going to end this with a quick exercise for you. The exercise here is a direct consequence of the result that we have just proved. Suppose that a and b are positive and n is a natural number. Okay, then the following is true. Then ab raised to 1 by n is a raised to 1 by n times b raised to 1 by n. What this means is that if a and b are positive numbers and n is a natural number, then the nth root of AB is in fact the product of the nth root of A and the nth root of B. Okay, so yeah, go back and using the fact that there is a unique nth root for any positive number, prove this corollary, right? So this is really just a corollary of the previous statement that I'm leaving as an exercise to you. Okay, so with that we'll end this particular video. And what we are going to do next is talk about some other aspects of the reals. Okay, at this point, we have essentially completed looking at some of the consequences of the fact that R is an ordered field which satisfies the least upper bound property and contains Q as a subfield.